So there are far more things we can do than we actually have time to do. And so I thought I would try to give you just a small smattering of possible topics. So the first possibility is several complex variables. And so I want to talk a little bit about that today, and then talk a little bit about one more way to do integration. So we're not going to have time to do details for everything. What I want to do is give you a little bit of a sense of where the subject goes, so that in the future you will have some sense of, do I want to learn more about this? As well as you never know when you're going to have a conversation where it's useful to have a little bit of depth. And so I've stayed in touch with a lot of former Williams students who have told me, every now and then X has come up, and one of them just told me something from linear programming came up in one of their graduate comp sci classes. The problem is I don't know what's going to come up for each one of you, which is one of the reasons why I'm doing this broad approach to complex analysis for the past week as well as this week, to just give you some sense of everything. All right, so several complex variables. So the other nice reason to do several complex variables is, of course, it provides a good way to review one complex variable. So in one complex variable, what's the fundamental region we study?
Complex plane.
Extended complex plane.
Okay, complex plane, extended complex plane, that's too global.
Open disk.
Open disk, unit disks, right? So one dimension, unit disk, or a small disk. Something like that. So the question becomes, what's the right analog for several complex variables? So it's not clear. So we can look at this as, the ball of radius r about a is the set of all z such that the absolute value of z minus a is less than r. So in n dimensions, z is now going to be z1 to zn, a would be a1 through an. So one possibility would be the sphere, is to look at, and how would I define the sphere?
The absolute value of all the complex variables either added or multiplied together is less than that.
I don't want to multiply them, because if one is 0, then that makes the product 0.
Added together.
So, okay, so did you say the sum of the absolute values?
Yeah,
That's not going to be a sphere.
you're right.
Now, you're actually right, that's the thing we want to study. The sphere would be squaring the absolute values and adding. We study the polydisk. And depending on whether or not you're English or British, you use either a K or a C, it doesn't really matter. So the polydisk is going to be the set of all z such that the sum of zi minus, I'm sorry, it's going to be this one, zi minus ai is less than ri. So this gives us a little bit more flexibility in that it doesn't have to have the same thickness in each direction.
Is it zi or is
zi minus ai.
no? It's a set of all zi such that.
No, it's the set of all z such that.
Oh, I got it.
Or if you want, this is probably bad notation, even though it's used. Why should I change my index to a K?
It's complex analysis.
Yeah, because it's hopefully clear from context, but just in case, let's use a K. This reduces to one dimension very nicely. And it turns out this is a useful analog. What results would you like to generalize?
All of them.
All of them. Right? If I have a result in one variable, I'd love to have the result in several variables. Okay? Santa does not have unlimited resources, especially in this economy. You need to prioritize. So when you're asking complex Santa, or several complex Santi, what to get. So we'll be studying the new holiday of Zemus. Right? Generalizing from the real case, from the real holiday. Right? So what would you ask for? What's your first theorem? Cauchy's theorem. Oh, So Cauchy's theorem. So Cauchy's theorem holds. And so you basically get an analog that f of z1 zn is equal to 1 over 2 pi I to the n. And then here you'll have z1 minus a1 equals r1, zn minus an is rn. Then you'll have f of zeta 1, zeta of n, over, then what would we have down below? Who remembers? So again, good way to review what we've done in one dimension.
Well,
Well, it would be zeta minus z.
So in one dimension it would be zeta minus z. So it becomes zeta 1 minus z1, dot dot dot, zeta n minus zn. And the proof is essentially to keep applying Cauchy's theorem again and again and again and again. Now, this is the crash course in complex analysis. I'm not being that rigorous. For instance, there's certain things I probably should have done before doing Cauchy's theorem. You never see a theorem without a statement. Or at least you should never see a theorem without a statement. Right? What's the statement of Cauchy's theorem?
A holomorphic function continuous in a closed separate connected disk.
Great. Excellent. So not only have you told me what kind of function I have, but you've told me where the function lives. So if I want to have a generalization of Cauchy's theorem, I have to know what does it mean for a function to be holomorphic, and where do I want the function to live. So what does holomorphic become? So I'm going to give you 3 statements. 1, holomorphic in each variable. 2, continuous as a function of n variables, holomorphic in each. And 3, analytic, i.e. series expansion is the function. I have to put it here. How many of you know what that stands for? Yes. Right, which is why I can't put it down here. Right? So you have to have the following are equivalent above the equivalent statements. Which one is easy to prove?
First one. 2 implies 1.
2 implies 1. Right? 2 implies 1 is pretty easy. If it's continuous as a function of n variables and it's holomorphic in each, and if that right. So 2 implies 1 is not so bad. The difficulty is these other stuff. And so again, we spent a lot of time working about is analytic the same as holomorphic? And that was a big theorem. How did we prove analytic was holomorphic? And this is a way to review what we've done this semester.
I think we used the special cases, like the special contours first, and then like with for that theorem, then we tried to generalize it. But
So that was proving primitives exist, and then that was proving that certain functions are holomorphic. And then that was proving Cauchy's theorem that certain integrals are 0. So all that stuff with special contours and Glossa's theorem, that was to get to Cauchy's theorem. Yes?
Was it 2 points with one of them just a little ways away, and you take a contour from one of them and you connect it?
No, that was to get a primitive. Right? So that's again going back to the Glossade and trying to prove that a holomorphic function has a primitive, the integrals along closed curves are 0. So let's say I have a holomorphic function. What theorem did I use to get my series expansion? It's on the board if that helps. Cauchy's theorem. So remember, So holomorphic equals analytic. What did we use? We used 1 over zeta minus z was like 1 over zeta minus a plus a minus z. So then that became the same as 1 over zeta minus a, and then 1 minus z minus a over zeta minus a. And then we could expand that using the geometric series formula. We used Cauchy's theorem, and we were able to then get a series expansion that converged. You can do something very similar to that here. Because we have a version of Cauchy's theorem in several complex variables, all we have to do is add k's. This is the advantage of being on the blackboard. Basically in half a minute to a minute, with then a lot of technical bookkeeping, you now get your series expansion. And the series expansion is called Osgood's lemma, at least in special cases. So again, I don't want to go through all the details. I want to give you a sense of what's reasonable, what's not reasonable. Hopefully something like this sounds reasonable. I can just keep doing things one dimension at a time. I can then series expand, and I can put everything like this. It seems reasonable. I should get results like this. So the question is, do you expect everything to be the same in several complex variables as one complex variable? How many of you enjoyed taking the SAT? How many of you still remember vaguely what the SAT was like? Did you have these things, rocket is to Armstrong as Nautilus is to...
I think they got rid of those analogies.
Did they get rid of those analogy things? So you guys didn't have to suffer through
They
them?
were dumb.
Yes. And by all means, this can be recorded and preserved for posterity. Right? But you've all at least seen those types of questions. Think back to what happened when we went from a real variable to a complex variable. Were things basically the same, or did new things emerge? Do you think new things will emerge when we go to several complex variables, or do you think all the newness has happened?
Probably all.
Seems unlikely
Which?
that all the newness has happened.
That all the newness has happened. So some newness might still exist. So there could be some things that change. So I'm going to need to recall some facts from Calc 3, from Green's theorem, Stokes' theorem days, which is dangerous, but I will try that. One-dimensional life is in some sense boring from an analyst's point of view. Right? We really don't have that many choices for paths. So let's look at geometry. One dimension. And let's say, here's my obstruction. That's a problem for some. I'll change it to a car. Alright, so I have an obstruction. Can I get past this obstruction?
Dimension.
In one dimension? No. In one dimension, I'm stuck. I can't get around it. And so fundamentally, there's huge difficulties. Removing one point can actually fragment your set and split it into two disconnected sets. All right, let's go to 2 dimensions. And so now, here's my obstruction. Here's root 2. Here's my car. And so there's a pedestrian blocking my path in route 2. In fact, there's a whole chain of pedestrians. Or they're having a sit-in or something. I can't drive straight down route 2. Am I stuck?
Let's take route 3. It goes around.
There's enough space between buildings. The buildings are not all connected. I can do some path like this. It's probably not going to be a nice semicircular path the way Williams has been built, but I can get around this obstruction. Right. So this is one of the places where 2 dimensions is very different than 1 dimension. And in fact, I can keep going, and I can come back to where I started. So right now, 2 dimensions is looking very different than 1 dimension. But there's something I can't do to this curve. What can't I do to this curve?
You mean the circle?
The circle.
Can't make it you can't condense it into a line.
Good. I can't.
Actually mean it?
I can't contract it into a point. I can't reduce it to a singleton. Why can't I do that? Yeah, because the obstruction is in the way. What about 3 dimensions? So now I have the same situation. What can I do now? I'm sorry?
You can pretend it's a sphere.
I can pretend it's a sphere.
Go around the other way.
Close. So I do like the idea of pretending I'm on a sphere. So I'll draw the sphere this way. So here's my obstruction at the center, and let's say I have the equator as my curve. Can I contract my equator to a point?
Yes.
How? Yeah, so I was picturing, but I'm kind of looking for this. Was that what you were doing? Or?
Yeah, I was trying.
Okay, so then send me an email. But yeah, I can contract up like this, and I can take the equator and just keep moving it. I mean, there are some people, we call them Australians, who would actually go downward, but you really want to move upward. Okay, and you can contract all the way to a point. So there's a fundamental difference in geometry between 2 dimensions and 3 dimensions. That this obstruction, in some sense, is avoidable. And if you look at the differences, this is really subtle. I'm not sure if you've seen this in Calc 3. But there are differences in trying to integrate functions with singularities and trying to use Stokes' theorem in 3 space versus Green's theorem in a plane in terms of what will you get. And it's because I can lift up my curve. Okay, so there is a difference in geometry. I am not skilled enough to draw 4-dimensional pictures that well. Even 2 dimensions seems to be hard for me. So the difficulty is it's very hard to visualize what's happening in complex analysis in higher dimensions. But it seems likely that there's going to be something that's happening with the different geometry. Okay. So it's called domain of holomorphy. And so a domain of holomorphy, basically, I don't want to go into the technical definition, is basically saying I have a set, and you give me any point on the boundary of the set, and I can find a function that's holomorphic in the region, but cannot be extended across the boundary at that point. Okay? So omega is a domain of holomorphy if given a point W on the boundary of omega, there exists a function f holomorphic on omega such that cannot analytically continue around W. So basically, the way you should think about it is, I can find a function that's holomorphic, but not holomorphic on a larger region. Now, of course, this is just saying I can't do it at one point, but there's going to be ways to combine difficulties at several points. So somebody give me a nice set where you have a function that's holomorphic in the set, but there's an obvious difficulty in continuing it further. So I want a function that's not holomorphic everywhere, but holomorphic somewhere.
Complex logarithm.
I'm sorry? Complex logarithm. That's more complex than I want. that would work. And so I can't continue it across the line. I want a simpler example than that, but the logarithm is a terrific example.
Not there's anything with a punctured disk.
Okay, so something with punctured disk. So give me a function on the punctured disk or the punctured complex plane.
1 over z.
1 over z. So I want the simple example. Okay? So, if I take f of z is 1 over z on c star, which is c minus the origin, or d star, which is the disk, the unit disk minus the origin. That shows that these are domains of holomorphy. I have a function that's holomorphic that I can't extend. Now here, the only boundary point of c minus the origin is the origin, so it's very easy. Here, well, I've got the boundary of the disk. And so, this function would work to show that I can't extend it inside to the origin, but maybe I can extend it past the boundary. And in fact, the function 1 over z does extend past the boundary of the unit disk. So the question is, can you give me a function that I can't extend past the unit disk? So let's study the unit disk. So if you do 1 over z minus 1, that's perfect. It is. The problem with that is I have the entire boundary, and you've just taken care of that one point over there.
But since can't the function depend on the point?
Yes.
So you can just do 1 over z minus your point.
Right. So what and so again, this then becomes a question of exactly what do we want the domain of holomorphy to be. So what you're telling me is you give me any point, and you can find a function. Can you find a function that works for all points at the same time?
Over absolute value of z minus 1?
So that means that's no longer going to be holomorphic because you put in the absolute value. So 1 over z minus 1 doesn't has problems right here.
So it wasn't that problems on the entire boundary of the disk.
On the entire boundary of the disk. Or we need a way to combine things that have problems. So take all the functions that have troubles and put them together.
No,
I'm sorry?
Z minus 1 times z minus I times z minus every point.
Okay, so you want to do a product? Okay, so if you're doing a product, I see at least one person rolling their eyes. That's not polite. If you're doing a product, that's not so bad. We can always take logarithms and convert it to a sum. But the difficulty is we need to make sure that the product converges to something that's not identically 0. So can somebody give me another function other than 1 over z minus 1 that has issues somewhere in the unit disk? Is this the only function that has a problem on the boundary? What else? I don't want absolute values. They're not allowed in my class. Yes?
Sin phi z?
I want a cousin of this. I've got 1 over z minus 1. Can you give me a cousin of
1
this?
over z squared minus 1.
Okay, that's taking a product.
No products, no signs. Has to be
So
present.
what's something that's very close to 1 over z minus 1 that will have a problem on the boundary?
1 minus z. 1 over 1 minus z.
That's the same function. I'm not going to let a little minus sign bother me. But what's really close to 1 over z minus 1? So this has a problem at the point 1. Can you?
Plus 1.
Yeah. 1 over z plus 1.
Oh, I thought we were letting negative sign bother us.
Depends where. See, that negative sign wasn't discriminating, it was hitting the entire function. So I have 1 over z minus 1 and 1 over z plus 1. Okay? If I add the two of them, am I okay? Is that still a holomorphic function? What's another function I could then add? So you've given me this point, you've now given me this point. What would be the next one?
C plus I.
Okay. 1 over z minus I.
Are we just going to add them all?
Well,
Sweet and troublesome.
now, what are you starting to worry about as we keep adding these things?
Infinite line.
We're going to have a lot of points, potentially uncountably many points. So this thing may not converge. So we could restrict ourselves to points on the unit circle where the angle is given by a rational multiple of 2 pi. There will only be countably many of those. These are the roots of unity. So we could look at just zeta of n is e to the 2 pi I over n. Just look at those points. Because if it blows up at those points, you give me any point, this set is dense. The problem is, can I add all of these together?
Still a lot of functions.
It's a lot of functions. So I can't just add them together. If I multiply them all together, the product could go to 0 inside the unit disk. What could I do instead of treating them equally? Weight them. So I'll weight this by 1. How much should I weight this by? 2. 3. A half, a fourth. Let's do a fourth. Oh, let's do a half. It's an extra.
Wrong direction.
Right? Well, no, it depends which way you're saying your weight.
Yeah.
But put in a factor of 1/4. What should the next one be?
1/9.
1/16.
So you could try 1/9, but then you're going to have to be a little bit careful, and you're working with a series that's, okay, 1 over n squared does converge, so you could probably make that work,
About 8.
but let's get extra decay.
8's 2.
I like 1 over 4 squared. Then 1 over 4 cubed.
I like that. 2 squared.
2 probably works as well, but let's give ourselves extra decay just to be safe. And so what you can do is you can take a dense set Zn and study the sum of 1 over 4 to the n, 1 over z minus the n. And if you look at that, this function will converge, and this function will blow up at points on the boundary. So I'll leave it to you to do the details of this. There's actually a simpler function to look at. And so I'll leave this one to you to really look at. G of z is the sum of 1 over z. I think this works. So look at z to the k factorial. Inside the unit disk, everything is fine. But I claim that as you approach the boundary, you give me any small arc on the boundary, and there will be a blow-up. And so think about angles with rational denominators, 2 pi over a rational number, or 2 pi p over q, stuff like that. So here actually zeta of n, I would actually need a little bit more than this. I would need to look at zeta of n squared, all the way up to zeta of n to the n minus 1. Because otherwise the zeta of n's, they're going to just cluster around over here. I need to just have them spreading out. But the idea is I can take a dense set of points, and with a dense set of points, I can construct a function that will blow up simultaneously at all of them. And so there is no way to extend this function anywhere. So think of it as you have infinitely many stop signs, and you are forced to stay confined in your initial neighborhood. So it turns out in one variable, any open set is the domain of holomorphy. You can always find a function that cannot be extended. What do you think happens in several complex variables? It doesn't happen. Geometry saves the day. And so, again, giving myself somewhere between 30 and 50 minutes to introduce several complex variables, what result do I want to get to? This seemed like a fun result to get to as to what goes wrong, what goes different. So the question is, do you think this is something that goes wrong, or do you think this is something that goes right? I think this is something that goes right. That functions can be extended. So let's consider 1 over z. in one variable, in one dimension. So this is the prototypical classic example of a function that blows up. It blows up at a point. I want a function that blows up at a point in several complex variables. So let's go to 2 dimensions. Blow up at the origin. So somebody give me a function that blows up at the origin. Okay. 1 over z1, z2. Anything else?
1 over z1 plus z2.
1 over z1 plus z2. Anything else?
1 over z1.
1 over z1. Anything else?
1 over z2.
1 over z2. What else?
Any multiple.
Yeah. Any multiple of these? I'll do one more. 1 over z1 squared plus z2 squared. That way at least I get on the board. Do all of these functions satisfy the requirement that they vanish at the origin?
Yes.
Do they all satisfy the requirement that they vanish only at the origin? No. Every one of them vanishes at more points than just the origin. It is impossible, it turns out, in 2 and higher dimensions.
Wait, do you mean vanish or blow up?
Oh, I'm sorry, blow up.
Oh.
Sorry, if I'm talking about the denominators vanish at the origin, the functions blow up. All of these functions blow up at the origin. But they also blow up elsewhere. And in fact, they blow up elsewhere in a connected way. So this function blows up in the plane z1 equals 0, z2 equals 0. This one blows up in the plane z1 equals minus z2. This one blows up, any value of z1. This one, oh, wait a minute. Sums of squares, maybe this one is okay. Maybe I did it. Oh, they're complex. Right? So for this one, if z1 equals I plus or minus I z2, it blows up. So this was trying to generalize the 1 over x squared plus y squared. So it turns out in several complex variables, if I give you a function on the punctured polydisk that is holomorphic everywhere but the origin, it has to be holomorphic at the origin as well. So can have a holomorphic function in polydisk minus the origin if have isolated. Okay, so basically you have a holomorphic function in the polydisk minus the origin. It is extendable to the entire polydisk. Okay. So the notion of a domain of holomorphy is very different. In some sense, these are all removable singularities. And the reason it comes down to geometry, it comes down to using Cauchy's theorem and being able to bypass the origin and moving up in another dimension. We don't have the ability to do these dimensional detours in one dimension. We are stuck. We can't contract the curve. The idea that we can contract the curve somehow allows us to avoid issues like this. Okay? So this is a brief introduction to several complex variables. It's an extreme... Yes?
So wait, don't you have like pole and exponential singularity?
So a lot of the theory generalizes, but you can't have an isolated zero, you can't have an isolated singularity. So in one variable, if you have an accumulation point, it has to be identically 0. In several complex variables, you can have accumulation points without being identically 0. So again, this is a... Yes?
So do we gain anything then going from, say, 2 dimensions to 3 dimensions?
I don't think so. I think the theory is basically the same, except maybe the geometry of the regions for the domain of holomorphy. The real change is happening once you have this ability to move up. But again, I'm not an expert in the subject, and so it could be the case that once you go to 3 dimensions, there's a new kind of U-turn that's allowable. in topology, there's often problems like this, where with really high dimensions we know the answer, with really low dimensions we know the answer, and there's this range of like dimensions 3, 4, and 5 where strange happens. And a lot of times, once you go up to a certain level, you have enough freedom in terms of the movement. And so here, once we go to several dimensions, we're fine. Okay, so this was a very brief introduction to several complex variables. For Wednesday's class, I want to do some fractal geometry, dynamical systems. What I want to do now is I want to end with some contour integration. And so this is the method called branch cuts. It's the least standard of all the methods in complex analysis. For contour integration, it's the hardest, but you should be at least aware of its existence. The first time I gave this lecture in, I guess the class was 302 back then, I did not realize how much analysis is required to estimate how small things are. And so it was supposed to be a 5 or 10 minute lecture, it basically took the entire class period. So now at least I know what's going to happen, and so I'm going to just say, see my notes for the details of how you bound it. So the online notes do not actually go through the details of how you bound everything. I've written up notes and posted them as to how you actually do the calculations. So let's let f of x be 1 over 1 plus x cubed. And I want to integrate from 0 to infinity of dx over 1 plus x cubed. So if you think about this, this could be a probability distribution, except for the fact that it doesn't integrate to 1. It's non-negative. It has finite integral. So if I want to make it a probability distribution, I need to figure out what does it integrate to so I can renormalize it. So I need to evaluate this integral. Okay. How do you think we should evaluate this integral?
Branch cuts.
Yes, exactly. No, you should be able to answer that question without even knowing what a branch cut is. Right? It's in the section on branch cuts. Right? Almost surely the way we solve this is to use branch cuts. So the question then becomes, why can't we use the other techniques we've studied? So why don't we just double the integral from 0 to infinity to be from minus infinity to infinity?
It's not even.
It's not even. So the non-evenness is really bad. There's another issue with doubling. Blows up on the negative real line. X equals minus 1. So that could be an issue as well. So there's a lot of problems with this. So the question is, how can we evaluate this? It turns out you can evaluate this using the techniques we've done. The way to do this using the methods we've done is to notice the fact that I have an x cubed. I could change my variables in a very nice way and not see a difference. What could I change x by? So I can't send x to negative x, that will change it. But I can send x to something, and I won't see a difference down here. So the hint is, this is a very well-crafted lecture. I was up till 4 a.m. working on this to make sure that what I'm doing now follows naturally from something we did earlier today. What could I multiply x by so that I don't see a difference between x cubed and ax cubed? So send x to e to the 2 pi I over 3 times x. Multiply it by a cube root of unity. Then I won't see a difference between x cubed and my new value. So what I could do is I could look at a contour like this. Such a great contour goes off the board. But I could do a contour like this, where I'm coming down now on this, and along here the denominator is going to be the same. The numerator will change by a constant factor. That's not a problem. I can use the bring it over method. Okay? You can bypass branch cuts and attack this directly. And the difficulty is you have to really think what's going on. X cubed, well, when is that not going to be changed? It's not going to be changed if I multiply by a cube root of unity. Right? I want to describe the branch cut. It's right. You may not believe me. Do you trust me as an honorable person who will not lie to you?
Sure.
All right. This is, you know, a color printout of my notes. They're online. You can download them. Wow, I haven't even gone into the surprising part. There was an issue with the printer. We've had lots of issues.
That I believe.
This is what I got for my section on branch cuts. And so I showed it immediately to Professor Johnson. And I said, look, you know, here's my picture with the cutout over here. And look at the paper. No, I mean, I actually prefer not to have it with a point like this. I actually prefer to do the semicircle. But I thought it was very interesting that the printout seemed to know that it was on the branch cut. So here's how the branch cut works. Here's the origin, not drawn to scale. Here's epsilon. And here's a semicircle of radius epsilon. And what I'm going to do is I'm going to look at the following path like this. So notice these lines are almost the same as on the real axis. They're a little bit off. Now my function has nice decay, so along the big circular arc it shouldn't be too bad. Along the little epsilon arc, hopefully it's not going to be too bad. The question is what function to look at. And so now I'm going to use your example from earlier today. So you had given me what function?
The complex logarithm.
The complex logarithm. So what we're going to do is we're going to let f of z be the log of z over 1 plus z cubed. Now the growth of the logarithm is very mild. So it's not going to be too bad. Now what's an issue with the logarithm?
You can't define it everywhere.
I can't define it everywhere. Can I define it in this region? Yes. I've cut out, right? Now is the name of this method now becoming a little bit more obvious? The branch cut. I'm working with a branch of the logarithm. I just want to label things the same way. So I'm going to call this gamma 1. This will be gamma 2. This will be gamma 3. This will be gamma 4. The integral over gamma 2 is going to be small. Right? You've got to do a little bit of analysis with the logarithm. I don't really want to go through that. You know, if we had 30 minutes, I would go through it. We'd have, I think, 6 minutes, 7 minutes, 6.5 minutes. Not really worth it with 6-7 minutes to do. But hopefully you believe small circular arc of radius epsilon, the logarithm is not going to grow too much. Basically, epsilon log epsilon tends to 0. So integral over gamma 2 small as epsilon log epsilon goes to 0. Integral over gamma 4 small as log of r, and then the length of the whole thing is going to be on the order of r. But I divide by r cubed, goes to 0. Right? So the length of this whole thing is on the order of r, 2 pi r, who cares, it's on the order of r. I have a 1 over r cubed from the denominator, right? And then the log of r, you know, in complex values, look, I can bound the absolute value of the log of z with the log of the absolute value of z. So gamma 4 is not going to be bad. I'm just left with gamma 1 and gamma 2. Now one of the problems is I have to figure out, you know, what is the logarithm at each of these points. So if I give you the point z is r e to the I theta, the log of z is the log of r plus I times theta. What I basically want to do is have gamma 1 and gamma 3 essentially differ by a constant when I have their total contribution. And so what I'm going to need to do is I'm going to need to figure out the log of these points. Well, I know how high up I am. And I have epsilon going, epsilon is fixed, I have x going from 0 to I. So this over here is the point x plus I epsilon. This is the point x minus I epsilon. and I can try to figure out what are their sizes going to be. I want to try to do this the exact same way I'm doing it in my notes to make it as easy as possible. All right. So we would get z plus would be rx e to the I theta x, and we would have z minus would be rx e, and what would its angle be? No, its angle is not minus.
Oh, right. We can't do that.
We can't do that. Okay, so correct yourself.
2 pi.
Yes. So it's the e to the I 2 pi minus theta x. Right? We've got to be careful as to how a thing is defined for the complex logarithm. It's not the minus. So now, if I look at the difference between the two logs, the log of z plus is the log of rx plus I theta. The log of z minus is the log of rx plus 2 pi I minus I theta x. Okay? And so what I want to do now is I want to look and see the integral from these. And so what I will get, if I look at the integral over gamma 1 plus the integral over gamma 2. Well, I've got to be careful because of how things are oriented.
So gamma 3.
Gamma 3, thank you. So gamma 3 goes from 0 to I. I'll have the log of z plus over 1 plus, and then z is going to be x plus I epsilon cubed. And then just dx. Now, over here, I have a minus sign because I'm going in the wrong direction. So I'll actually subtract off the log of z minus over 1 minus x minus I epsilon cubed dx. Okay? Let's see how much time is left. Okay. So we've only got about a minute left. So I don't want to go through all the details. So I've written up the full details. Let's see what's going to happen. Ideally, you'd like to just say, screw the epsilon, just view it as 1 plus x cubed and 1 minus x cubed. If I do that, well, when I have the log of z plus minus the log of z minus, notice the log of the rx's will cancel. And now when I'm looking at what goes on for the other one, here I have I theta x with a plus sign, here I have I theta x with a minus sign. So I'm going to be a little bit careful. But how big is theta of x? The angle is really small. So even if I have an integral of a theta of x to do, it's not going to really bother me. This whole thing is r, which is huge. Epsilon, right? So the angle of theta x is very small. So theta of x is damn small. So even if I have to integrate it over something of if I have to integrate it over something of length r, maybe I have some issues, right? Because this whole thing has length r. And so if this is small, but I multiply by r, so this is where the technical bookkeeping comes in. Okay? Damn small, but is it small enough with respect to r? The 2 pi I is going to be beautiful, because that'll just live over here, and then that will give me my answer. And then, of course, the question is, does this function have any poles? The log of z over 1 plus z cubed. Phew, right? What would happen if it had no poles? It would be 0. Oh, and the only thing that's left is 2 pi I times the integral I want. I'd be very worried. But because it has poles, those poles will then have residues. And that will then be the integral I want. And so everything will work out. Okay? So this is a brief introduction to branch cuts. It's a very powerful method. It's a lot more work. There's a lot more analysis that needs to go in. And so I've written things up in full detail. This is not just sloppy notes, talk about complex variables. I've written up the calculations in full detail with all the analysis that you need for the bounding. So I'm happy to chat with you more about stuff like that. Okay, so we will continue with complex dynamics on Wednesday.